You know you're stripping from your pain. You know you're sinning from your sin. Whenever heaven's doors are shut, you get them open, but I know you. Give me steam, and how you feel can make it real. Real as any place you'll be. Get along with the dreamer's dream. Stay back. So stay back. Can't you see I've lost control? I'm getting to scream. You're moving in so close, still I'm picking up this heat. This heat. Give me steam. I'm how you feel can make it real. Real as anything you've seen. Get along with the dreamer's dream. You know you're green from your red. You know the quick from the dead. So much better than the rest. You think you've been blessed, but I know you. You know your letter from your snake. You know the throttle from the brake. You know your straight line from a curve. You've got a lot of nerve, but I know you. Give me steam. I'm how you feel can make it real. Real as any place you'll be. Get along with the dreamer's dream. Everybody knows style. Hold your breath, count to 5, act slap, booby trap, cover it up in bubble wrap, room shake, earthquake, find a way to stay away. It's gonna blow, it's gonna break. This is more than I can take. Oh yeah, I need steam.
All right, so today we start on the final module for this course, final topic, which are trees and tree-based data structures. And we've already seen some data structures here, but the whole point of data structures is that they have structure. And with this structure, you can exploit it for potentially efficient operations, right? And that's going to be our motivation here. What we want is we want a data structure that supports efficient CRUD, right? Remember, create, retrieve, update, and destroy. We want to be able to put stuff into the data structure, pull stuff out, update stuff, delete stuff from the data structure. So ultimately what we're going to focus on are retrieval, search, insertion, and deletion, right? So we want those operations to be efficient. Let's look at the data structures that we've already looked at and review why they are not sufficient, right? With linked lists, insert or delete at the head or even the tail, if you kept track of the tail in the variation, one of the variations that we looked at is constant time, right? That's going to be order 1. Why? Because all it involves is creating a new node and changing a couple of references. Once you've done that, you've chained together into the linked list, updated the head or the tail or whatever, right? However, arbitrary insertion or index-based search was going to be linear, right? Because to get to the middle element or the ith element, you had to start at the head and you had to traverse I times. And we saw that doing that would have taken 20 years to sum up 1 billion numbers, something like that, right? Then we looked at array-based lists. Or they were just the opposite, right? I guess we looked at array-based lists first. But here, if you want to do an index-based search, it's going to be order 1 because you have random access. If you want the ith element, you know where the array starts. It's all contiguous. It begins at this address. You know how many bytes each one thing takes, and so you know the memory offset and can jump there immediately by just doing some arithmetic, right? Or at least that's how the computer does it. We also saw that if it's sorted, we can exploit that structure. If it's sorted, we can use binary search to do order log searches, right? And so that's even better. That's better than linear search. But of course, if we were doing unstructured that wasn't sorted at all, then we'd have to rely on linear search, and we're back to order n. In fact, inserting or deleting from the start was also order n because it's linear, right? Why? Well, if I've got a million elements in there, I don't want to put something new at the beginning. I have to shift everything down in order to make room for it, right? So they're kind of, the linked list and the array-based list, they're kind of opposites of each other. One thing becomes efficient on one, another thing becomes inefficient on the other. We then looked at other data structures, stacks, queues, and decks, right? All operations were always efficient, right? Well, but there was a restriction there, right? But this was only because they were restricted access data structures, right? You could only work at one end or the other end or both ends or some variation thereof, right? Because we restricted how you could do this, then everything was going to be order one, right? Because you could do it with a linked list and always working at the head or the tail. Those are going to be order one operations. But you cannot do arbitrary CRUD. You can't arbitrarily insert something into the stack. If you did, of course, that would knock over all the dishes, and that would be a completely different data structure. You're not shopping for a stack anymore. You probably want a list, right? And then we're back to the linked list and array-based lists. But our ultimate goal is a general purpose data structure, right? That allows us to put stuff in, take stuff out, search, et cetera, such that everything is efficient. We want all of those operations to be efficient. Now, trees provide a potential for those efficient operations. We're not going to get there all the way. I'll show you how you can get there all the way, but that's going to be a CS3 topic, basically, a data structures and algorithms topic. Before we even get there, though, we need a lot of terminology and basics, right, of notation and stuff like that. A graph is a collection of nodes, or sometimes we call them vertices, right, and edges that connect pairs of nodes, right? Generally in computer science, we call them nodes because they're actually storing data, and it's more than just a vertex that, it's this circle or whatever, right? It actually has data inside that circle, and so we call them nodes. But in graph theory, pure graph theory and mathematics, they call them vertices. But we both call them edges, right? So for example, let me go ahead and bring in just a graph over here, right? Where's my graph? There it is. Here's a graph, right? Okay. How many nodes does it have? Well, it has 1, 2, 3, 4, 5, 6, 7 nodes, right? We denote that usually with n, right? N is going to be our variable that we're going to use as to denote how many vertices there are. Now, m is going to be the number of edges. How many edges are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I think. Hopefully I didn't miscount, right? But we're going to use those two variables there to denote those two things, right? Again, generally, n is going to denote the number of vertices, and generally we use m to denote the number of edges, okay? Also for us, we're going to only consider simple undirected graphs. So edges are undirected. If I have an edge going from A to B, then that's the same as the edge going from B to A. And we depict that over here as just a bunch of lines connecting these things, right? For example, this one, it's undirected. Now, if it were directed, you would actually put an arrow on it. That would imply that you can go from D to B, but you cannot go from B back to D directly. Those would be called directed graphs, but we're not going to consider those. We're going to consider undirected graphs here. So my first observation here is, what are the maximum number of edges? What are the max number of edges you can draw in a graph, in an undirected graph? Okay. So let's come over here and think about that. Okay. First of all in this example, not all the edges are there. For example, there's no edge between A and B, right? There's no edge between A and C, right? So let's think about this more generally. What if I gave you a graph with just one vertex, excuse me. There's my vertex. Can you draw any edges here? No. Now, there are things called pseudographs where you can have a self-edge, and that is a thing. That's especially a thing with stochastic processes or Markov chains or whatever, where you have a probability of going from one state to another state, from one node to another node. And then you also want the probability of it staying at the current node. So you can have this self-loop here. But we're not going to consider those pseudographs, right, or those fake graphs. Right? Now, what if I gave you 2 nodes here? 1, 2. Right? How many edges could you draw now? 1. Why? Well, you had to choose one endpoint, and then you had to choose the second endpoint, and then you had to draw the edge between them. What if I gave you 3 vertices here? 1, 2, and 3. Now, the process that I'm going to do this is I need to choose a starting point and choose an end point. I could choose this one and this one, making this edge right here. Or I could choose this one, and I could make an edge right here or an edge right there. Right? So here, or sorry, this should have been n. Let's go ahead and get rid of that. N here as m is 3. So don't think that they're always going to be the same here, though, because if we go up to 4 here, it's going to look very, very different. Right? If I had 4, 1, 2, 3, 4 vertices here at nodes, right? Then I could do 1, 2, 3, 4, 5, 6 edges. M is equal to 6. Right? Now, do not confuse this crossover point here with a vertex, right? That's just this edge going over here, and then this edge is going under it. If you want to, you can redraw it over here, right? Those are something called planar graphs, but once you get up to n equals 5, then it's no longer planar, okay? Now, let's reason about this a little bit more generally, right? Suppose that I had n vertices, right? And there's just a whole bunch of vertices here, right? Now, to draw an edge means that you choose one endpoint, and then you choose the second endpoint over here, and you draw them together. I'm going to appeal to combinatorics. I don't know if you've gotten to this in 235 yet, but you've probably seen it before. Something that looks like this. I want to choose 2 vertices among n of them, right? And this is n choose 2, right? So I have n things here. I've got n vertices sitting all over here. There are n of them. I just need to choose 2 of them, and that defines one edge. All right, choose 2 more of them, and it defines another edge. Choose 2 others, and that defines an edge as well. Right? You might have seen C2n or CN2 or something like that. Hopefully, you've seen that before. That kind of combinatorics. So, what's the formula for this thing? Right? This is going to be n times, and we won't derive it. I'll just give it to you. N times n minus 1 over 2. That looks remarkably familiar at this point, right? We've seen this now in several different algorithm analyses. Insertion sort, worst case. Selection sort, right? Any case, right? Because the controlling term here is going to be n squared. In other words, it can be very, very dense. It can be very, very complex. So if I go from a small graph, like 1, 2, or 3, or 4 vertices, and I went up to a graph with, say, 1 billion vertices, then how many edges would there be? Well, there'd be 1 billion times 1 billion minus 1 divided by 2. There'd be a lot. Processing a graph that large would then take us back to our algorithm analysis, where it took us 20 years to do something like that because it's quadratic here. Right? In other words, generally, graphs can be very, very complex. Okay? Let me go ahead and copy this observation here. Right? And the answer is... There we go. The maximum number of edges in a graph is going to be n. N nodes is going to be n times n minus 1 all over 2, which is going to be order n squared, right? In other words, generally, graphs can be dense, right? And it's quadratic. So even small graphs, they're going to blow up in complexity with respect to the number of edges as they get more and more dense. We don't want that. We want a little bit more structure, so we're going to impose some structure here. And we're only going to consider trees. A tree is a connected acyclic graph, a graph with no cycles. Right? First of all, we need some terminology here. What is a path? Right? A path is a graph. In a graph is a sequence of connected vertices. Come on, there we go. There we go. Now it's showing up. A graph is a path in a graph is a sequence of connected vertices. Right? We also need to know what the length of a path is. The length of a path is the number of edges on it, which is equal to the number of nodes minus 1. So let's take a look at an example. Let's use that same graph that we had before. Where is it? Let's bring in that graph, right? And let's identify one or a couple of paths here. I can go from A to D to F to E. What's the length here? Now again, the length is going to be the number of edges on it, 1, 2, and 3. I can go from A to D, I can go from D to F, and then from F I can go over to E, traversing each one of those edges. It's 1, 2, 3, which is equal to the number of vertices minus 1, because if you look at your fingers and ask yourself how many gaps you have between those fingers, that's the relationship there. Right? You can also start at a different vertex. Let's go from B to G, to D, to C, to F, right? The length here is going to be, I guess I never said it before, but the length over here is 3, the length over here is 4. You have 5 vertices, 4 edges connecting them. Now be careful. You could go from A to D to F, back to D, back to F, back to D, back to F, and then over to E, right? Basically what you're doing here is you're going to A to D, then D to F, and you're going back and forth and before you go over to E. Why would you ever want to do that? Right? You're trying to find other data. Why are you wasting your time going back and forth and back and forth? We're not going to do this. Instead, we're going to restrict our attention to what are called simple paths and simple cycles. Those are things that do not traverse the same edge more than once. All right? So, what have we learned so far? We're only going to consider simple paths, right? Those that do not traverse the same edge more than once, because it's pointless. You're doing a lot of busy work going back and forth, and you're not achieving anything, right? A cycle is a path that begins and ends at the same node. So, for example, over here, let's go ahead and erase all these now. There we go. Give me a cycle here, and I'll highlight it in green. I can go from A to F to D back to A. There is the cycle right there, right? So in other words, A to F to D, right? Now what is the length of this cycle? The length is going to be a little bit different, because remember the length of a path is the number of edges on it. I guess it's not going to be different, but it's going to end up at the same vertex here, and so the length is going to end up being 3. That's different from a path because that's going to be equal to the number of vertices, right? We have 1, 2, 3 vertices, but the actual cycle goes from A to F to D and then back to A, right? There are other paths here, or other cycles, excuse me, right? Is there a cycle of length 4? Well, we can go from A to F to E. Let's see. Something interesting here. No, I don't know if there's a length 4, but there's certainly a length 5. Oops. Let's draw it that way. Right. So that's 1, 2, 3, 4, 5. Right. That's a cycle of length 5, and it consists of A to D to B to E to F back to A. Right. And by the way, it's the same forward or backwards. So you could say F to E to B to D to A. That's the same cycle. You could also start at a different location. I could start at F here instead, and I could go from F to E to B to D. Or I guess I did start at F, didn't I? Let's go ahead and start somewhere else then. Let's go ahead and start at B to E to F to A to D. And that's the same as that cycle right there. Those are all the same cycles. Okay? So the length of a cycle is equal to the number of edges on it, which is equal to the number of vertices or nodes on it. Okay. It also has to be connected. Okay. You could have graphs that are disconnected. Let me show you an example here. It's not going to be this one because it is connected. But what you could do is you could draw, say, a bunch of vertices over here that have some sort of connection to each other, and then a bunch of vertices over here, right? There we go. But I can't get from this vertex to any vertex over here because the graph has been disconnected. Right? Now, if you have a collection of trees, that's called a forest, but we're not going to consider forests. We're not going to consider disconnected graphs. We're only going to consider connected graphs. A disconnected tree is called a forest, but we're not going to consider those. Right? So now that we've given this some structure, how can we exploit that structure? The way that we're going to exploit that structure is by making some observations first. Right? Trees are not all that complex. In a tree with n nodes, there are exactly n minus 1 edges. Now, why is that? Right? Let me come over here and let's go ahead and review the same graph that we had just before. Right? Let's go ahead and add that graph right there. And let me go ahead and expand it so that we can see it. And let me go ahead and start removing edges. Because is this a tree? No, we already identified several different cycles, right? So let's go ahead and start getting rid of these cycles. Right? I'm going to go ahead and get rid of that edge because I remember that it was involved on a cycle. It was involved on a cycle from A to F to D. Right? That cycle has now been broken. Okay? But that's not all. Right? How many more edges do I need to remove to break any other cycles? Give me another cycle, A to D to G to E to F. Well, I just need to break it at one edge there. So let me go ahead and break it right there. Now, there are still cycles in this. Give me another cycle. Maybe that one right there. All right. Let's go ahead and get rid of it by getting rid of that. There we go. All right. Do I still have cycles? Yep. D to E to G. So let's go ahead and get rid of that one right there. Right. That's because that there was a cycle right here, but now that cycle is gone. Right. I still see a cycle here, so let's go ahead and get rid of D and G. Right. Are there any more cycles? Yeah. What? 1, 2, 3, 4. Right? There's a cycle of length 4. Let's go ahead and break that one. Let's go ahead and break it like this. Doesn't matter how, I'm just doing this as an exercise. Are there any cycles left? Well, let's count up the number of vertices. Right? Remember the number of vertices was 7, right? 1, 2, 3, 4, 5, 6, 7. Now, how many edges are there? I see 1, 2, 3, 4, 5, 6, 7. Is there a cycle? Did I miscount these? 1, 2, 3, 4, 5, 6, 7. There's a cycle in here somewhere, isn't there? I'm miscounting something. Does anybody see the cycle? C, G. Thank you. C, G, where? B, D, F, back to C. There we go. Thank you. Right? It was difficult to see because I was just randomly getting rid of crap. Oh, come on. That's way too thin. There we go. All right. Now I've got what I was saying before where it is 6 edges there. All right. Let's look at another one. Here is the same graph, but edges have been removed in a different way. Here is an actual tree. Where is it? There, unoriented tree. There we go. Right. There's the same graph, but I removed edges in a different way. And again, if you count these up, then the number of vertices is going to be 7, and the number of edges is going to be 6. Now that goes back to what I just said here, that in a tree with n nodes, there are exactly n minus 1 edges. Can there be fewer? Right. So let's do that same exercise here on the tree. What if I were to remove one of these edges right here? Any one of these edges? Right. What happens? There's now a disconnect. There's one component, and then there's the other component that's over here. Right. This one right here. So removal of one edge necessarily disconnects the graph. We're not going to consider that. All right? So let's back this up. All right, fine. Well, can there be more? Right? What if I were to add one more edge here, say from A to C? Right? What did I just do? I induced that original cycle that we observed first, right? So the addition of any one edge is going to induce a cycle. The removal of any one edge is going to cause it to be disconnected. Right? So that's why, I mean, that's not a proof, but that's why we have this observation. The removal of any one edge will disconnect the tree. Any additional edge will induce a cycle. Right? Thus, in a tree, the number of vertices, or the number of edges, is always going to be proportional to the number of vertices or nodes. It's going to be order n, not order n squared anymore. We put a restriction on it so that it's no longer this dense thing where it would take 20 years to process it. Instead, it's going to take a linear amount of time to process anything in a tree. Also, another observation here is that in a tree, oh, come on, slow today. In a tree, the number of paths between any two vertices is exactly 1. In other words, there is exactly one path between any two pairs of nodes. Right? Now we can prove that a little bit, just a proof sketch here. Right? Suppose that were false. That's too thick. All right, suppose that there were an edge A, or vertex A, and a vertex B, and suppose that there was one path between them, path 1. Now suppose that there's another path, because what we're doing is we're going to by a proof by contradiction here. Suppose that there are two paths. Right? There's this other path over here, P2. Right? What have I just had? What is this now? This is a cycle. It's no longer an acyclic graph. It's no longer a tree. So by way of contradiction, we have that this is true. There's exactly one and only one path between any two pairs of nodes. Could it be 0? If it were 0, then that would mean that you have a disconnected graph. And again, we're not going to consider those. All right? All right. Those are very good observations, but we also need some additional structure here to make them appropriate for a data structure. Trees can be oriented top to bottom, left to right. Let me show you how. All right? Let's just go back to this one right here. All right? Get rid of that. All right? Now what I want you to do is imagine that I could pull this out of the two-dimensional screen here. Suppose that I did that with respect to D here. I grabbed D, pulled it out of the screen, and then dangled it and let gravity dangle all of the nodes down below it. It would look something like this. Dangling off of D would be A, right here, because of that edge right there. Dangling off of A would be E and F. Right? Dangling off of E was nothing because that's the end. Okay. Dangling off of F, however, would be what? C, then G, then B. And that's not the only orientation. Right? There are many other orientations. We could do the same thing, but we could do it with respect to A here. If I pulled out A from the graph, dangled it all down, then I would have E, D, and F below it. Right? E terminates, D terminates, but F hanging off of that is just as before, C, G, and B. Right? That's another way of writing it top to bottom, left to right. And note what I did here. When I was writing it left to right, I went in alphabetical order. Oh, I did not. All right, there we go. That should have been what it was. Right? Let me go ahead and correct that. It's not that big of a deal. D and E. I tried to go in alphabetical order. All right, there we go. That's because so our trees are going to be are going to weirdly grow downwards, right? That's actually not that weird. Think about your family tree. If you were to write out a family tree, who's up here? Your ancestors. Who's down here? The descendants, right? It grows downward, and that's how our trees are going to grow, right? So that gives us some additional nomenclature here, or additional terminology. At the top is a single node called the root. The root is at the top. In real trees, the root is at the bottom, and it grows upwards. Our trees, the root is going to be at the top, and then they grow downwards. Right? Nodes under a tree are called children, just like a family tree. Right? If you've got parents, then they directly below them, they have their children. And then from their children's perspective, you've got a parent node right there. right? Any node with 0 children is what's called a leaf, right? Because if you grow a tree up and then it terminates, there are no longer any branches. What's at the end? That's a leaf. But a node in this case, because it grows downward with no children, is also called a leaf. You can talk about parent-child relationships, right? You can talk about ancestors, descendants, grandchildren, grandparents, cousins, et cetera, et cetera. Right? That's still not enough. We want more. We want more structure. So what we're going to do is we're going to limit the number of children. Suppose that each node is limited to at most 2 children. In other words, you could have 0 children, in which case you are a leaf. You could have 1 child, or you could have 2 children. Not only that, but we're going to orient them left to right. Right? You can have a left child and or a right child oriented left to right. That means that you have 4 possibilities. You could have neither child. Come on, save. There we go. You could have neither child, in which case you are a leaf. You could have, this is a leaf. You could have a left child, but no right child. No right child. Right? You could have a right child, but no left child. Or you could have both children, okay? And this, finally, is called a binary tree. Right? And that's what we're going to work with, binary trees, binary search trees eventually. So let's go ahead and get rid of this tree, and let's look at an actual binary tree, oriented top to bottom, left to right. There we go. There it is. Okay? Now let's make some observations here. First of all, what's the root? It's the thing at the very top, A, right? Let's highlight all the leaves in, what happened to my highlighter, by the way? That one? Yeah, okay. Undo that. Let's go ahead and highlight all the leaves. Leaves, there we go. Oh no, I guess my pen should have done that. This is going to be a leaf node. There we go. So L is a leaf node. Why? Because it doesn't have any children. L, R, N, O, P, Q, and K there. They're all leaf nodes. Okay. What about C? Is that a leaf node? Well, it doesn't have a left child, but it does have a right child. Okay. You have other things like I that has a left child but no right child. Those are not leaves. Those are what are referred to as internal nodes. So let me change my color here to red, and that'll be my root. All others are internal nodes, right? So all of these guys right here, they're all internal nodes because they're neither the root nor are they the leaf, right? So there's some terminology there. We need some more definitions though. So when we talk about distance in a tree, we're talking about depth. So the depth of a node U is the length of the unique path from the root down to U, okay? So let's go ahead and get rid of all this, and let's understand what the depths of each one of these things are, okay? All right, so we can look at each node individually, A, B, C, D. We'll do them all eventually, but let's look at the depth. I'm going to jump ahead here to B. When I look at B, there is a unique path from the root node down to B, and the length of that path is 1. Right? Likewise to C, the depth of C is going to be 1 because of the length of the path. Let's fast forward here. What about R? There is only one unique path, we've already established that, from the root node to R, and it is of length 1, 2, 3, 4, and 5. All right? So R has a depth of 5. What about D, E, and F? They all have paths of length 2 from the root, and therefore they're at depth 2. What are the things at depth 3? Well, all you have to do is look how we actually drew this graph. G, H, I, J, K. So G through K. L through Q, they all have depth 4. I left one blank here. What is the depth of A? What is how far do I have to travel from the root to get back to the root there? I don't have to travel at all, do I? What's the depth? 0. Right? So by convention, the depth of the root node is 0. Okay? The depth of all the others is the length of the unique path. Right? Finally, the depth of the tree itself, is the maximal depth of any node in the tree. Right? In this case, the deepest node was R, and so the depth of this tree was 5. T's depth is going to be 5. Now that can change. What if I got rid of that node? Right? What if I severed that and it went away? Now the depth has changed. Because this is no longer there, the maximal depth is now 4, and so this changes to 4. Okay? Those are all the terminologies. Okay? All right, so with the remaining time today, let's do some math. How can we exploit this structure? Okay? Suppose you have a full binary tree, right? That is every node, let's go back over to our notes, right? Suppose you have every node is present. In other words, you have every child, you have both, every node has both a left and a right child up to a depth of D, right? All right? If we can develop a way to insert, retrieve, or delete elements from a binary tree such that all operations are proportional to the depth of the tree, right? And the depth of the tree is limited. The depth of the tree is limited, right? Or small. I'll quantify small here shortly. Then all operations will be efficient, or as efficient as the depth goes, right? So let's come over here and start doing some math. If I have a full binary tree, what does it look like? Okay. Well, at the first level here, at the first level I have, that's too big. There we go. At the first level I have one vertex. So at depth 0, the number of vertices, or number of nodes, let's call them, is going to be 1. Now if I go down one more depth, and everything is present, so we have both a left child and a right child, then at depth 1 I have 2 nodes. Follow this pattern. In the next depth here, or the next level, that's level 2 or depth 2, then I have 4 nodes. Right? Do we start to see a pattern? How many nodes will be in the next depth? 8. Right? And I said that it was full up until you get down to some terminus. It's not an infinite tree, right? You get down to depth D here. Tell me, how many nodes are going to be at that depth following this this pattern here? 2 to the D, right? Oops, come on. Not tracking. There we go. Finally, it's tracking. 2 to the D. Okay? So what is the grand total? Right? What is the summation of, and I'll use I here, of 0 up to D of 2 to the I? That's because each one of these was, 2 to the 0, this was 2 to the first, 2 to the second, etc., all the way down to 2 to the D. So what is the total, sum total of all of these? What is the total of powers of 2 plus ... plus 2 to the D? Right? Well, first of all, what is this thing called? It's a series. The summation is a series. But what kind of a series is it? How is it growing? Exponentially. We call that a geometric series. Right? And there is a closed form solution for this for general. If I said that this was base B, right, B would be involved. But since it's 2, all our bases are 2 in computer science, it actually greatly simplifies. This is going to end up being 2 to the D plus 1 minus 1. Okay? So now that's my number of nodes, n. Remember, n was our placeholder. That's our variable to express the number of nodes in a tree or in a graph generally. So what I want to do is I want to solve for D. because that will tell me what the depth is, right? Or what the, proportional to n. There are n things in this thing. What is the depth here? I need to get that in terms of n, right? So solve for d here. Take 1 to the other side, 2 to the d plus 1. Right? How do I get rid of that 2? How do we get rid of it with respect to a binary search? Log of n plus 1, base 2 implicit. And here I'm going to immediately take 1 onto the other side, and there's my d. Right? In other words, d is going to be order of log n. Does that look familiar? What's the only other algorithm that we've seen so far that achieves this efficiency? Binary search. Right? This is a binary tree. Right? The depth can be binary. Right? And so in terms of the number of nodes, a full or nearly full tree can have a guarantee on its depth that it'll be no more than log n. So if we can find operations that are proportional to that depth, and we can keep that guarantee, right, then we've achieved our goal, right, because of this analysis that I just did. Right? We're not going to get there yet, right? We are going to get here, where I'm going to show you all the operations that you can do on a tree that are going to be proportional to the depth, but you're going to need data structures and algorithms to use what are called balanced binary search trees, right? So we're not going to have a guarantee on the depth. Let me show you why. What if I had a skewed tree? What if I had A, B, C, D, right, E, dot, 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 right? In other words, suppose that I had, Z, right? What is the depth on this tree? Just did my ABCs, A through Z. That means that the number of nodes is going to be 26. Number of edges is going to be 25. What is the depth? What is the length of this path then? This is going to be 25 as well, right? In other words, here the depth is going to be order n, right? It's going to be proportional to those. In fact, what is this thing right here? I put it at a 45-degree angle. What if I didn't? What if I twisted it around so that it was straight? It's a linked list, right? So there's the connection, right? That if you have a skewed binary search tree, you're back at square one with a linked list, and everything is going to be linear again. Right? That's a skewed binary search tree. Right? We can do a little bit more here. Let's go ahead and start doing these things in Java. First of all, let me go ahead and create a new binary search tree to see how we would end up programming these things. Binary tree, sorry. And I'm going to immediately parameterize it so that, because I learned my lesson from our list data structure demonstration where I don't want to have an array list for integers and one for doubles and one for strings. I'm going to parameterize it so I only have one implementation for everything. Right? Now, what is in that binary tree? Well, what if I kept a list of everything in the tree? Back at square one. It's no better than a linked list or an array list. The only thing that you're going to keep track of in a binary tree is the starting point up here, the root. Okay? Well, what is the root? Is the root an element? So private T root. It's not just the element. It's not just like A in that tree that we just did. What else is it? Let me go ahead and just grab one of these things, these nodes, right? D right here, right? What else does D have here? Has a left child, has a right child, and if you want to go both ways, it has a parent. So it's not just the item, it's not just D being stored in there, right? It's a whole bunch of things. It's in fact a whole binary tree node. Right? Just like a linked list, you only kept track of the head, right? And the head was had other things. It had a reference to the next. It could have a reference to the previous one, right? So that's another thing that we need here. Let's go ahead and create a new class. There we go. And binary tree node, T. There. Now what's in that binary tree node? Everything that I just mentioned. It's going to have an item, that actual data, private T data, or item or element or whatever you want to call it. In fact, I like element a little bit better. Element. Right? It also is going to have a reference to the parent. Private binary tree node parent. And it's going to have a reference to its left child and its right child. I'll call it left child and right child. Right. And there is the start of our design for a binary tree. We'll get to search trees later, but a binary tree in Java. Okay. Now over here, binary tree node, T. I need to give it a name, I guess, and that name would be appropriate to call it the root, right? And it's not T over there. There we go. Okay. All you're going to do is keep track of the root. Now, as a thought experiment here, how are you going to search this tree? I want to find J, for example, right? Because I want the data stored at J. Well, if I can only start at the root, I now have two options. It's not like a linked list where you only have one option. Just keep moving forward, keep moving forward, keep moving forward. I could go this direction, right? And if I went that direction, then I would go all the way over here, and I wouldn't find J because it's way over here, right? I need a way of backing up, coming back up here once I've explored this entire subtree, and then exploring down this direction here. So we're going to have to be a lot more clever and a lot more systematic about this than a linked list, because a linked list, you just have to blindly keep going forward. This is going to require a little bit more thought, right? And we're going to look at 4 different ways of doing it: a pre-order traversal, post-order traversal, in-order traversal, and a breadth-first search traversal. Each one of them has their own applications. Each one of them has their own advantages and disadvantages. But at the end of the day, if you're searching through this entire tree, you're searching through n things, and it's going to be linear, right? Again, it's not proportional to the depth, because you go down here and you don't find what you're looking for. We're going to need to have even more structure eventually in order to achieve our goal. Right? But this is a good start, and when we come back next time, we'll more fully flesh out this design here, and then we'll also talk about those traversal strategies that I just hinted at. Right? We'll do that on Wednesday.